Welcome, everyone, and thanks for joining today's first talk in our multi-part series on interpreting veterinary literature. Over the next 15 minutes, we're going to tackle one of the most misunderstood concepts in all of clinical research, the p-value, and its much more useful partner, the confidence interval. By the end of this talk, you'll have a solid mental framework you can apply immediately the next time you pick up a journal article. No memorization required, just understanding. Let's get started. A roadmap for the next 15 minutes. We'll start with p-values because they dominate the veterinary literature, but we'll quickly move to confidence intervals, which give you far more actionable information. Then we'll do a quick case at the end to practice. Ready? Let's go. We can understand the p-value, we need to understand what question it's actually answering. Every study tests a null hypothesis, which is basically the skeptic's position. Assume there is no difference between the drug and placebo. Assume everything we see is just random variation. The p-value then asks, if that were really true, if the drug did absolutely nothing, how often would we see results this extreme or more extreme just by chance? So a p-value of 0.03 means if the null were true, there's only a 3% chance we'd get data this surprising. Critically, and this is the number one mistake, the p-value is not the probability that the treatment works. It's the probability of your data given that the null is true. That's a very different thing. Look at this number line. As we move left towards 0, our data becomes increasingly inconsistent with the null hypothesis, meaning it becomes harder and harder to explain our results by chance alone. The 0.05 threshold is a convention, not a law of nature. Ronald Fisher proposed it as a rough guide in the 1920s, and it stuck, but p equals 0.049 and p equals 0.051 are not meaningfully different, yet one gets published as, quote, significant and the other doesn't. Here's the big clinical trap. A study with 10,000 dogs might find that drug X reduces lameness scores by 0.1 points on a 100-point scale with a p-value of less than 0.001. Statistically, very significantly, clinically, useless. No owner would notice that difference. This is why we need confidence intervals. Confidence interval tells you two things the p-value cannot: how big the effect might be and how certain we are about that estimate. A narrow CI means the study was large and well-powered. We have a precise estimate. A wide confidence interval means there's a lot of uncertainty. The true effect could be much larger or much smaller than the point estimate. The key question to ask is, does the confidence interval cross the null? For a mean difference, the null is 0. For a ratio, like an odds ratio or risk ratio, the null is 1. If the CI crosses the null, the result is not statistically significant. But more importantly, read what's inside the confidence interval. If the upper end of the confidence interval just barely crosses 0, the true effect is probably small. But if it crosses 0 with a wide swing, there's real uncertainty. Here's a visual example with 3 hypothetical drugs. This is a kind of plot you'll see in forest plots and summary figures throughout the literature. Drug A. The CI is entirely above 1 and doesn't cross the null, statistically significant, and the effect size looks meaningful. Drug B. The CI crosses the null. We cannot rule out that the drug does nothing, not significant. Drug C. Borderline. The CI barely crosses the null. This is where you need clinical judgment. Look at where most of the confidence interval sits. Is even the lower plausible bound clinically meaningful? Get comfortable reading these plots. They show up everywhere. Drug trials, meta-analyses, survival studies. The four traps I see most often when clinicians read papers. First, a non-significant result does not mean no effect exists. It might just mean the study was underpowered, too small to detect an effect even if one is there. Second, significant does not mean important. Go back to that large-scale lameness example. Third, always ask about sample size. A study of 12 cats with a p-value of 0.04 should raise your eyebrows. Small samples produce unstable, unreliable p-values. Fourth, always look at the actual data. What are the means? What are the raw numbers? A p-value without context is almost meaningless. Read the case and let's work through this together. We have a well-powered RCT of 480 dogs. The new NSAID outperformed placebo. Statistically, P equals 0.03, so it clears our conventional threshold. But look at the confidence interval, zero point 0.1 to 0.7 points on a 100-point scale. Even if we believe the most optimistic estimate, we're talking about less than 1 point of improvement on a 100-point scale compared to placebo. Is that clinically meaningful? Could a dog owner or a clinician detect that difference? Almost certainly not. The answer here is no. You should not recommend this drug based on these results, at least not for this outcome. The study demonstrates a statistically significant but clinically insignificant effect. This is exactly why we read both the p-value and the confidence interval together, and why we always ask, so what, after seeing a significant result. The key takeaway: statistical significance is a starting point, not a conclusion. Clinical significance requires your judgment. Up. The p-value is a tool, useful, but easily misread. It tells you how surprised you should be by your data if the null were true. It does not tell you the probability that the drug works, and it does not tell you whether the effect matters clinically. Confidence intervals are your best friend. They give you a range of plausible values for the true effect. They show you precision, and they let you apply clinical judgment. Always look at both. Always ask, how big is the effect and how certain are we? In Talk 2, we'll move into drug trial design, RCTs, blinding, randomization, and how to read a forest plot. See you there.